Faraday's law of electromagnetic induction. In this topic, we will discuss the following subtopics: simple demonstrations on electromagnetic induction, Faraday's law of electromagnetic induction, mutual induction, alternating current generators, direct current generators, Fleming's right-hand rule, transformers, and application of electromagnetic induction. Introduction. In this topic, we shall look at the generation of electricity from changes that take place in a magnetic field. Simple simulations used to show electromagnetic induction. Case 1. A magnet moving into a coil. The animation below is a simulation about electromagnetic induction when a magnet is inserted into a coil. Click on the play button and make your observations. Observation. When the magnet is moved into the coil, current flows, making the pointer to move. Explanation. When there is relative motion between the solenoid and the magnet, the solenoid cuts through the magnetic field lines, that is, magnetic flux, which causes an induced electromotive forces, EMF. When there is no relative motion, the solenoid does not cut the magnetic flux, hence no induced EMF. Case 2. A coil inserted to enclose a magnet. The animation below is a simulation about electromagnetic induction when a coil is inserted to enclose a magnet. Click on the play button and make your observations. Observations. When the coil moves into the magnet, current factors affecting the magnitude of the induced EMF. The experiment below can be used to demonstrate the factors affecting the magnitude of the induced EMF. The animation below demonstrates these factors. To make your observations, click on the play button. Observations. When the magnet moves slowly, a small EMF is induced into the coil, creating a small current, hence a small deflection on the galvanometer. Increasing the speed of movement increases the rate of cutting the magnetic flux, thereby inducing more EMF, hence more current. The pointer therefore deflects further compared to the previous one. Conclusion. From the demonstration, the induced EMF and hence current is directly proportional to the relative motion between the conductor and the solenoid. The rate of change of magnetic flux is therefore directly proportional to the induced EMF. This relationship was first established by Faraday and is commonly known as Faraday's law of electromagnetic induction. In Lenz's law, Faraday discovered one of the important laws of electromagnetic induction. The animation below has been used to illustrate and explain the law. Play it and make your observation. Observation. When the magnet moves into the solenoid, the pointer moves to the left, while when the magnet moves out of the solenoid, the pointer moves to the right. Explanation. When the magnet is moving in, it induces a current in the solenoid which flows in a direction to induce a similar pole at the end of the solenoid to the approaching pole of the magnet and vice versa. This similar pole opposes the movement of the magnet, which causes the induction of an EMF. This idea is summarized in Lenz's law, which states that an induced current flows in such a direction as to oppose the change producing it. Mutual induction. Mutual induction is the process of inducing an EMF in a coil due to the changes in magnetic flux taking place in a neighboring coil. Observation. When the switch in the primary coil is closed, current is induced in the secondary coil, which flows in the anticlockwise direction, making the pointer to deflect to the right, then goes back to zero. When the switch is opened, current induced in the secondary coil moves in the clockwise direction, making the galvanometer pointer to deflect to the left, then back to zero. The deflection in the second case is greater than in the first case. Explanation. When the circuit is switched on, current tends to build from minimum to maximum. This creates a gradual change in flux, which causes the galvanometer pointer to deflect minimally. When the circuit is switched off, there is a rapid change in magnetic flux from maximum to zero. This causes a greater deflection in the pointer of the galvanometer. Fleming's right-hand rule. The relationship between the direction of induced current and the direction of the field and the motion of the conductor is summarized by the Fleming's right-hand rule. The animation below shows this relationship. Click on the play button to make your observations. Observation. When the conductor moves inwards, a current is induced which flows in the direction shown. When the wire changes direction, the current flows in the opposite direction. The animation above brings a modification of Lenz's law into what is called Fleming's right-hand rule. The rules state that if the thumb, the first finger and the second finger of the right hand are placed mutually at right angles, with the first finger pointing in the direction of the field, while the thumb points in the direction of motion of the conductor, then the second finger points in the direction of the induced current. Generators. In Form 2, we learnt about an electric motor in which a current-carrying conductor in a magnetic field experiences a force which causes motion. In a generator, motion of a conductor in a magnetic field produces an electric current. There are two types of generators, namely an alternating current AC generator and a direct current DC generator. Simple AC generator. Click on the play button of the animation below to observe how a simple AC generator works. Observation. Let the coil be originally in a vertical position with respect to the magnetic field. The curve moves from the origin to the maximum when the coil becomes horizontal, having completed a quarter turn. When the coil passes the horizontal and goes towards the vertical, completing a half a cycle, the current decreases to zero. As the cycle continues to three-quarter cycle, the current changes direction up to a maximum in the negative direction. As the coil completes the cycle, the current moves back to zero. Explanation. When the coil is vertical or perpendicular to the field, the wires of the coil do not cut the magnetic field lines, resulting in zero induced current. As the coil rotates to the horizontal position, it starts to cut across the magnetic field lines, and an EMF is induced in the coil. In this quarter, the number of field lines being cut increases from zero to a maximum, causing the current to increase to a maximum. When the coil passes the horizontal position, going back to the vertical, completing a half cycle, the induced current decreases to zero. This is because the number of magnetic field lines being cut by the coil decreases to zero at the vertical position. As the coil continues to rotate in the third quarter, the current increases again from zero to a maximum in the opposite direction and then reduces from a maximum to zero in the last quarter cycle as per Fleming's right-hand rule. This process is repeated with current changing direction every half cycle. Simple DC. The main difference between an AC and a DC generator is that the AC generator has slip rings, while the DC generator has a split ring commutator. Play the following animation to observe how it works. Observation. Starting with the coil in a vertical position with the edge AB uppermost, the induced EMF and current through resistor R increases from 0 to a maximum when the angle theta increases from 0 degrees to 90 degrees. Then factors affecting the magnitude of induced EMF. The following factors affect the magnitude of induced EMF: the speed of rotation of the coil or magnet, the number of turns of the coil, the strength of the magnetic field, and winding the coil on a laminated soft iron core. Play the animation below and observe how each of these factors affect the induced EMF. Transformers. A transformer is a device that transfers electrical energy from one circuit to another by electromagnetic induction between the two coils. One of the coils is named the primary coil, while the other is the secondary coil. A transformer changes the magnitude of the input voltage or current. The primary coil is connected to an alternating power supply. As the magnetic field in the primary coil changes, due to the alternating current, it induces an EMF in the secondary coil, which in turn causes an induced current. Types of transformers. There are two main types of transformers, namely step-up and step-down transformers. Step-up and step-down transformers. There are two main types of transformers, namely step-up and step-down transformers. Play the animation to observe the major differences between the two. Energy losses in a transformer. Since a transformer is a machine, it cannot be 100% efficient, and the following energy losses are normally experienced in normal situations. Eddy currents. The alternating magnetic flux in the soft iron core as a result of the AC in the primary coil causes a reverse current called eddy current. This causes a heating effect in the core, leading to energy losses. This is normally minimized by laminating the core. Flux leakage. Not all the magnetic flux in the primary coil is linked to the secondary coil. This causes a reduced induced EMF in the secondary coil. This is minimized by winding the secondary coil over the primary coil. Hysteresis loss. The repeated magnetization and demagnetization of the core due to the alternating current causes a heating effect. This is minimized by use of a soft iron core. Heat loss. The resistance of the coil and the eddy currents created during the magnetization and demagnetization process causes a heating effect which causes a loss of energy in the transformer. This can be minimized by using thick copper wires of low resistance and laminating the soft iron core to reduce the eddy currents. Efficiency of a transformer. A transformer is a machine in which power is introduced at the primary coil and delivered into the output circuit through the secondary coil. The efficiency of a transformer is expressed as efficiency equals to power output divided by power input multiplied by 100, which is equal to power in secondary coil divided by power in the primary coil multiplied by 100, which is equal to IS Vs divided by IP Vp multiplied by 100. The efficiency of a transformer is never 100% because some of the energy is lost in form of heat.